Okay, so in this video, we're going to continue sections 11.2, which is vectors in space. Before I get into the continuation, I do want to go back and clarify something I neglected to clarify in our last video. So we talked about defining a vector based upon a terminal point, initial point, P naught and P1. So what I'll do is I'll just sketch those same points that I used in the last video, or as close as I can. So we had some point P naught with coordinates X naught, Y naught, and Z naught, and then another point P1 with coordinates X1. Actually, I should have used X1, Y1, and Z1. So, and this P naught was our initial point. The P1 was our terminal point. So remember what we do is if we want to visually represent this, we have a line segment between the 2 points, and then we put an arrow at the terminal point to indicate that would be, if we had, say, a velocity vector, that would be our direction of travel. So now the reason I'm bringing this example back up is because I talked about moving a vector, but I didn't specify doing that with a set of coordinate axes. I just did it in the air, but I want to kind of do it with a set of coordinate axes. Let's see, my marker's a little bit too long, but we're going to pretend that my marker and that vector are the exact same length. So let's just pretend that they are for a second. So I talked about moving a vector so that its initial point, which is this point right here, this initial point is at the origin. So this vector, what I would do is, as long as I don't change its magnitude and direction, I'm going to take the initial point, which for us is this point right here on the marker, and I'm going to take it and I'm going to move it, and I can move it wherever I want to, as long as I don't change its magnitude and direction. So I can move it here, I can move it here. But to make representing the vector easier, what I'm going to do is I'm going to take it and I'm going to move it, and I'm going to take this and I'm going to make this touch the paper right there at the origin. So that's what I meant when I talked about in the last lesson, moving a vector. As long as you don't change its magnitude and direction, you still have the same vector. So I move it and I put its initial point at the origin. And now what I can do is I can represent this vector by whatever that point is right there. So now the name of this vector would just be whatever this point happens to be right there. Now, how does that happen? It's just by you doing the computations that I gave you all in the last lesson of doing x1 minus x naught, y1 minus y naught, z1 minus z naught, and that's going to give you precisely that point right there, whatever that point is, which we don't know. We can't explicitly see it directly from those, but if we do that computation, x1 minus x naught, y1 minus y naught, and z1 minus z naught, it'll give us what that point is. So I just wanted to clarify that a little bit before we continue with 11.2. All right, so now in continuing from 11.2, let's talk about how do we find the magnitude or the length of a vector. So given a vector A with components A1, A2, and A3, the length or norm or magnitude, you'll rarely hear me use the term norm, but I will use magnitude a lot. So length, magnitude of A is the length of A. So that's how we denote that. It's just two vertical lines on either side of the vector A. Please make sure you use vector hats when you're writing your vectors and you don't leave that off, because without a vector hat, then it's just a number. And a vector and a number are two very different things. And this equals the square root of A1 squared plus a2 squared plus a3 squared. All right. Note that the length or magnitude of A is just some number. So we take the square root of these components, the sum of the squares of these components, and we're just going to get a number. So this is no longer a vector anymore. Once you take the length of it, you just get a number. Now we tend to call those scalars instead of calling them numbers. So, but scalar, number, same thing. It doesn't matter which term you prefer, which term you use. So note that the length of A is a scalar or number. So the length of a vector is no longer a vector. Now there's an important length that we oftentimes like to have for vectors, which is a vector of length 1. So we've given those their own name. A unit vector is a vector whose length is 1 the unit vector in the direction of a vector A is 1 over the length of A and then times the vector A. And we haven't seen multiplying a scalar by a vector, so we're going to go ahead and show you what I mean by that. So that is the vector A1 divided by the length of A1. So all we do is we're going to take all the components of the vector A and we're going to divide them by the length of A. So divided by the length of A, comma, A2, we divide it by the length of A. And A3, we divide it by the length of A. And now we have a new vector. This vector, it points in the same direction as A, but it has length of 1. So if we said that, say my marker, whatever, was a vector and it has length, length 3, for instance, then if I wanted a unit vector that points in the same direction, well, we'll say my marker has length 2. If I want a unit vector that points in the same direction, I would take the length of my marker, which is 2, and then I divide all of the components of my marker by 2, and I get this new vector, which has length 1, but it points in the exact same direction as the original vector that we had. So oftentimes we want a unit vector, and this is how we go through and we compute a unit vector given a vector A in the first place. So let's look at an example just to kind of break up the monotony of doing definitions. So let's look at page 120 in your textbook. We will do, let's see, number, actually, we'll come back to an example that we need a little bit more terminology before we can do it because they're using unit vectors. And let's introduce writing vectors in terms of unit vectors, and then we'll do that example. So 3 important unit vectors. All right, let's make a set of coordinates, or actually I'll tell you what they are and then we'll sketch them after I tell you what they are. All right. I, the vector I, the component 1, 0, 0, the vector j, 0, 1, 0, and the vector k, the component 0, 0, 1. So now if we sketch these on a set of coordinate axes, so all of these vectors I, j, and k, they all have length 1. So the vector I is on the x-axis, but it has length 1. So we'll just label that I. And the vector j is on the y-axis, and it has length 1. And the vector k is on the z-axis, and it has length 1. So now what we can do is we can rewrite, we can introduce a new notation for writing vectors using this I, j, and k instead of using these brackets. So that's what we'll talk about next, is how do we represent a vector using that I, j, and k instead. So let A be equal to the vector with components a1, a2, and a3, and b be equal to the vector with the components b1, b2, b3, and c be any scalar. Oops, if I could spell scalar. All right, so first we'll talk about adding two vectors. So a plus b, and adding vectors is fairly straightforward. You just add the corresponding components and you get a new vector. So when you get the new vector a1 plus b1, and then the second component is a2 plus b2, and the third component is a3 plus b3. So we add two vectors, we get a new vector, which is just its components are the sum of the corresponding components in the two vectors we were given. And then multiplying vectors, c times the vector a, all we do is we multiply each component of a by the value c. So we get a new vector again is ca1, then comma ca2, ca3. So now with these tools and our unit vectors, we can introduce some new notation for writing vectors. And you'll have to be comfortable with all of the different notations because you'll see all of them in your textbook. A, our vector A that we were given, so a vector with components A1, A2, and A3. Now we can rewrite this as in this form, or actually let me write this in one more form up here. So we could also write this as C times and actually write out the vector. So this and this and this all say the same thing. You could see any one of the three. I'm going to use this right here down here. So this A, what we can do is we could rewrite this as A1 times the vector 1, 0, 0 plus A2 times the vector 0, 1, 0 plus A3 times the vector 0, 0, 1. So now why can we rewrite this is that because notice if we do A1 times vector 1, 0, 0, we'll just get the vector A1, 0, 0. Here we'll get the vector 0, A2, 0, and here we'll get the vector 0, 0, A3. And if we add those three vectors, because we add corresponding components, we will get precisely that vector right there. All right. So now we've rewritten A as a sum of three vectors. And notice that these three vectors that are in the brackets, those are our important unit vectors, I, J, and K. So now we can rewrite the vector A as, so this is a new notation that I was talking about that you may see, A1 times I plus A2 times J plus A3 times K. So all three of these are important ways to represent the vector. And just for good measure, let's look at it one more way, which I mentioned, but I didn't write up here in the list, is if I go ahead and put that A1 in there, we also could write this as A1, 0, 0 plus 0, A2, 0 plus 0, 0, A3. So if you were to see this, this is the same as that right there. So if you wanted to write that as a sum of three vectors using the pointed brackets, you could write it that way. So please make sure you're comfortable with all three of these different notations for writing a vector. So now I think we do have everything we need to go back to the example that I said I wanted to do. So let's go back and look at number 14 from your textbook. So number 14, they write the problem using this notation. So that's why I had to hold off, because we didn't know this notation yet. So we are on page 720. And we're looking at number 14, which says, in exercises 14 through 17, find a unit vector having the same direction as the given vector. Okay. So they give us the vector A is equal to I plus J minus K minus K. All right, so that's the vector they give us. They want us a unit vector that points in the same direction. Now, I, J, and K are unit vectors, but I plus J minus K is not a unit vector, or we don't necessarily know if it's a unit vector or not. The only way we figure out is by finding the length of the vector. So that's the first step in this problem, is that we need to find the length of the vector. And then from there, we can determine a unit vector that points in the same direction. So let's just rewrite this another way. This is also the same as our first notation. Now, in our first notation, this, remember, is 1, 0, 0. So that vector is just going to put a 1 right here, and it's going to put zeros right there. This vector is 0, 1, 0. So that will give us plus 0 right there, and it will give us a 1 right there, and it's not going to give us anything in the K component. Then this right here is going to give us a negative 1. So we could write that way. Now, if we wanted to go a longer route to get to this same thing, you could say, okay, well, this is 1, 0, 0 plus 0, 1, 0, and then minus the vector 0, 0, 1. And when you put these three things together, you will get precisely that, because 1 plus 0 gives us our 1. 0 plus 1 minus 0, oops, I think I said plus, but I meant minus, give us a 1 there, and then 0 plus 0 minus 1 gives us our negative 1. So either notation is fine. So now what we're going to do is we're going to find the length of this vector. So the length of A is equal to the square root of A1 squared, which is 1, plus A2 squared, which is 1, plus a3 squared, which is also 1. So we get the square root of 3. So that tells us, because the length of A is not 1, that tells us A is not a unit vector. But we can find a unit vector that points in the direction of A by using our formula of 1 over the length of A, then times the vector A. This is going to be, we take the components of A and we divide each one of them by the square root of 3. So 1 over the square root of 3, 1 over the square root of 3, and then negative 1 over the square root of 3. So I tend to use the bracket notation just because I think it's probably easier for students to work with than the IJ and K notation, because computationally, this is a little bit easier to see what the numbers are versus that. So that's why you'll see me use the bracket notation more so than the IJ and K notation. But please make sure you're comfortable with all of the different notations. All right, so the next thing that we'll look at is resultant force, and we'll also look at what it means for two vectors to be parallel. But I will introduce those couple of things in our next video, because resultant force takes a little bit more effort than some of the past things that we did.